All right, welcome everyone to the second COMSOC video seminar. If you don't have a speaking role right now, I would like to ask you to please mute yourself. We'll work a little bit better. We have two great speakers lined up for today, and I'm very much looking forward to that. Before I introduce them, I want to say a few things about what's going to happen in the coming weeks. So next week we have another kind of seminar in the standard format such as this one with two speakers, Agi Che and Remzi Sanver. For the week after that, we have invited Haris Aziz to host a session, and he will look for speakers. And our rationale was not only that he is famous for his exquisite taste, but also he's based in Sydney, where it's probably midnight or something like this right now. And so the idea was that he might be in a position to organize it at a time that would be a bit more convenient for the other half of the world's population. So that should be nice, and maybe a bit more difficult for some of us to make it, but we'll make an effort. And for the week after that, we have a very special thing in mind. And if you can already guess what it's going to be, you're welcome to reveal that deep knowledge of the COMSOC community in the chat right now. So what we're going to do then is we're going to have a rump session. So rump session, many of you know, is this thing where probably 10 people can give a 5-minute talk each. And sometime next week, I will put on the website a form where you can volunteer to do that. And then if we don't get 10 volunteers, I will appoint a few additional speakers to make up the 10. And if we get more than 10, then we'll somehow have to find a fair way of picking 10 people. And so that's a way to very quickly get lots of people say something interesting. It's always a lot of fun if we do it in the real world. I'm not sure how it's going to work in this format, but we're going to try. Okay, so that's the preview of what's going to happen soon. Then for today, very similar to last time. So last time, several people afterwards said they didn't manage to figure out how this thing with raising your hand works if you have a question after talk. So we would like to explain that now. If you, for most of you, this will be probably at the bottom of your screen near the middle, there's something that says participants. And next to it, it says 130, because right now we are 130 people. If you click on that, then something else should open, and you can also either do that, or you can, in the menu, there's a view menu, and there you should also be able to see something that's called participants. Then you see the names of the participants. That's not the most interesting thing for you right now, but below that you see some buttons. For example, you see a yes button and a no button, and you see this blue hand. And if you click on the blue hand, then you're indicating that you would like to raise your hand and have a question. So just to make sure that when I'm getting through, could I ask everyone to raise their hand right now, just to make sure? Oh, yes, indeed. Well, half of the people found it. So I think that's good enough. We cannot handle so many questions anyway. Okay, then please lower your hand again. So press the button again, so all the blue hands go away. Many of them are away already, not all of them. So that afterwards I will actually see whether you have a question. Yes, almost there. Okay, with questions, we're going to do it in a similar way as last time. If you have questions during the talk, you can type them into the chat. So this might be a clarification question. And actually last time it wasn't always clarification questions. They still work because other people took it upon themselves to answer those questions. So we have, in both cases, we have co-authors in the audience who might be able to answer, or anybody else in the audience who has an opinion. They're very welcome to reply in the chat. So this chat also goes together with the recording on the website afterwards, and it's quite interesting to have a look at that. So please use that. If you are, I think because there might be a lot of information in the chat, I think it would be very useful that whenever you have a question, rather than just an answer, that you type it in like this, all caps question, and then your thing. And if you're quite confident that what you have to ask is not really, can you please justify everything you've just done and how do you compare with my own work? But if it's really a clarification question, then you might preface it like this with the word clarification, uppercase, and then it will be a bit easier for us to find it afterwards. And maybe even the speakers will spot it and respond on the spot, or maybe somebody else will answer for them. When we get to the end of the talk, I will invite you to raise your hand if you have a question, or you can also type your question into the chat. And then if I pick it up, I might read it out, or I will invite you if you want to then say it yourself after you've seen that you have an interesting question that you've typed into the chat. As always, it's always better if people keep their questions really short and to the point, then several people can ask one. Okay, very good. So I think we are ready to start with the first speaker. It's my great pleasure to introduce to you Piotr Faliszewski, who will be our first speaker. Piotr is based at the AGH University of Science and Technology in Krakow. Very nice place. Some of you will have been there in 2012 when he organized the COMSOC workshop, so that was very nice. Many of you will know his work, so he in particular worked a lot on the computational complexity of bribery and control problems in voting, starting from his PhD. And in recent years, he's been very active in work on multi-winner voting rules, both the algorithmic aspects and the axiomatic aspects. And today he's going to tell us, I believe, something about how you might, in a principled way, generate some data to test your ideas that you have about voting on that data. And I would like to invite Piotr to please share his screen.
Sure. So, hello everyone. Before I start, let me mention that this is a full screen friendly talk, which means that you have this gray area somewhere around here. So if you go into full screen, probably maybe somewhere here you have a button showing full screen. You can go there, you can put the windows, the chat to the gray area. It will never be used on the slide, so you don't lose anything. This talk the title is Drawing a Map of Elections. It's joint work with Piotr Skowron, Staszek, Szufa, Arkadii, and Nimrod. I believe Arkadii and Staszek are here. And Staszek will try to answer questions on chat if they appear. Okay, so let's start. So this talk has started from the observation that so in computational social choice, we have lots of problems that we are working on. This is winner determination, this is maybe robustness, margin of victory, all sorts of bribery, control, manipulation, possible winners, and so on. Also things related to axiom satisfaction. So you may ask how often Condorcet winner actually exists, how often this and that axiom is satisfied or not, and plenty of others. And historically, in the early days of COMSOC, we essentially proved that these problems are NP-hard. Then we started proving that they're also polynomial time satisfiable, or they have approximation or FPT algorithms. And over recent years, we started doing much more experimental work. And I would say that there's some problem with doing experimental work in COMSOC. Because you need some input for this. The input is usually a profile of ordinal preferences. So in this talk, we will often have preferences shown like this with colorful characters. Sometimes we will change the names of characters and we'll use monsters. But in any way, most of the problems we're dealing with essentially as input require a profile of ordinal preferences and maybe a little bit more of extra information. So for example, in a bribery problem, you might still say that you're asking if it's possible to make a particular person a winner. But still, the profile is the most important part of the data. Where does preference data come from? Well, thanks to Nick Matei, Toby Walsh, and all the Preflip team, maybe that's just them, we have collected quite a lot of real-life data. It comes from Formula One, from sushi preferences, from Dublin elections, from Netflix. And that's very nice, but it leads to, I believe it leads to serious problems. I mean, it's very often you can use this data well, but often problems arise because usually there's very few candidates between 3 and 20 and closer to 3 than to 20 in most cases. The other problem is if you actually want to test an algorithm, for example, from a multi-winner, I don't know, a proportional approval voting rule, and you take data from Netflix, well, that's nice, but this is maybe not how people actually would have voted if they were given this particular rule to use or particular application, which means that there are cases where real life data is actually somehow raises problems. So on the other hand, we have synthetic data. And here, the somehow sacred tradition of COMSOC by now was mostly to focus on impartial culture, the EARN model, maybe the Mallows model, and usually the papers that that use statistical cultures, they often invent or provide some extras on top of these kind of three basics. And here, the benefit is that we can always generate the size of elections exactly how we like it. The problem is, okay, is it any realistic? And the short answer is obviously not. Is it realistic enough? Who knows? Maybe sometimes. I mean, but which data, which model to use in which case? That's quite often unclear. Mallows model is maybe one example where it's usually clear that it should be used, but for the others, maybe less so. So what we want to look at in this talk is essentially we want to try to analyze elections generated from statistical culture. We're focusing on 100 candidates and 100 voters because this is the kind of data we were most often using for multi-winner voting elections. And it just seems kind of big enough to show things that we care about. But of course, other sizes are possible and could be handled similarly. Okay. So we want elections to be as varied as possible. But what does it mean? So, okay, so essentially, if we cannot have realistic data, we at least want to have varied data, so that you know, maybe we miss the actual realistic thing, but we hit many things around, and thus our algorithms, if they perform well on test data, they still perform well in practice. Okay, so a question that we have to ask when we're trying to find a set of diverse elections is how to measure similarity. And to measure similarity, there are many approaches. So when we started thinking of this nearly 2 years ago, maybe I think about 2 years ago, it was a different paper then. If we are given an election, we're given another one. So for now, we're focusing on elections of the same size, which means the same number of voters, same number of candidates. The number of candidates and number of voters do not have to be equal. It just happens to be an example. So if we have the colorful characters and the monsters, how do we say, are these similar or not? Well, I don't know. So one first step, we probably want to make a mapping of candidates so that the names of candidates become the same. Okay, I can map candidates one way or the other. I tried in some way. Okay, but if I generate data from statistical cultures, the order in which the voters come is completely meaningless. It just happens to be generated in one way or the other. So I may also want to map the voters. But in this case, I may want to swap some of them. Now I have a nice one-to-one mapping between the candidates, between the voters. But still, we have a problem because this final pair is actually not exactly matched to the vote on the other side. And that means that I still have to make a swap. I have to make the final changes in one election of the other. So now I can see with a proper mapping of candidates, proper mapping of voters, and with a single swap, so the distance is actually one swap, I can get distance over elections. And this is what we actually did a year ago, not in this paper. And the conclusions were that this is a really nice definition of a distance. It's NP-hard to compute. Who cares? I mean, NP-hard, I mean, that's where fun begins. Now we can actually do nice things. Except it's actually hard to approximate. And if we approximated distances, it's already maybe not so great. And it's FPT computable, but these algorithms, I mean, okay, 100 to the power of 100 to the power of 100, maybe not as bad, but something on this order. Yeah, it's FPT, it's publishable, it's not usable. Maybe it will become usable soon. Okay, but we have ILP, and God, it just doesn't work. I mean, maybe we're not competent enough, but we tried various tricks of using ILP solvers of various other heuristics, and we just can't do it. The problem is just plain tough. And so, test complexity 1. As a proud student of Lane Hammer-Sprandra, I could say, even when complexity wins, it's great. In fact, of course, for our task, we thought that we need a different metric. And this is what we did. We invented what we call a position-wise distance. So this is a relatively important slide. At least it tells you what distance we will be using for. Now, if we have 2 elections, this happens to have 5 candidates, 3 voters. We have another election. How can we measure their distance? Well, for each candidate, we come up with a vector of features. So here, this vector of features says that this character here comes from I guess a German story from Berlin. I can tell you in person when we finally meet what story it is. But this person arrives on position 2 once, on position 4 once, and on position 5 once. So we add 1 to these positions, and in other places we leave zeros. And we compute vectors like that for the other candidates. We do the same for the candidates on the other side. And then for each possible pair, we compute earth mover distance. So in this case, you see that if we move this one position, this costs 1, then we move one more one position, and next one 2 positions. Altogether, this costs 4. And this way, we were able to obtain exactly the vector on the other side. So this is how we computed the distance between this pair. We do it for every pair, so for this character and for every other character. Now I'm not showing the distances for all of them. And finally, we find best matching, lowest cost matching, and the sum of the distances gives me my distance. In this case, it's 1 plus 0 plus 0 plus 4 plus 5. So I know that this is now the distance between these elections. And this is what I will be using. However, how good is it? Well, we tried to test. So I told you that the Spearman isomorphic distance I showed before is bloody tough to compute. So we tried these elections of 8 voters and 8 candidates. This is about the biggest we can test. We generated a bunch of elections. I will not give you details how they're kind of related to the later part of the work. So for now, trust me that we generated a lot of elections. Now, each point on this plot is a pair of elections, and you have a distance in one metric, a distance in the other metric, and you can see that this kind of looks linear. This is more or less, this kind of shows that for these small elections, we're probably on random elections. We're not too far from this isomorphic distance we wanted. Of course, this is exactly because these are random elections. If we had something more complicated, we could be completely off the scale. But for random elections, it seems we're doing fine. Okay, so now we have a metric. We want to get on with drawing a map. We have to choose some elections to work on. Let's start with the, I don't know, notorious tree, which is impartial culture. So in impartial culture, we just choose votes uniformly at random. Then we have the Polya-Eggenberger urn model. In this case, we start with an urn where every possible order of preference arrives. We draw an order, and this one is selected, and some alpha times number of voters already in the urn return. So here is example for alpha equals to half. So this is how the urn model works. I guess many of you are familiar with that. And the Mallows model works similar, well, a bit differently. We have a probability of generating a vote V is that if we choose some center order if we have some certain center order, we can make swaps within this order. And the probability of generating a vote is proportional to phi to the power of number of swaps. So more graphically, we have a center order which is selected with somehow weight 1 over the sum of all weights. Now there are votes that can be generated from this order with a single swap. So each of these comes with single swap, and each of them comes with weight phi. Then with phi square we have more, and so on and so on. If we take phi equal to 1, then of course everything becomes impartial culture. If we take phi equal to 0, we have a single preference order. Okay, so we have these three ways of generating orders. We were often asked, how come we're not looking at impartial anonymous culture? The answer is very simple. We have 100 candidates. Impartial anonymous culture and impartial culture are essentially the same from practical standpoint for this case. Okay, so we generated a bunch of impartial culture model and Mallows model elections, and we used an algorithm to draw them on a flat surface. We used Fruchterman-Reingold force-directed algorithm, and what we got is this. Now this requires some discussing to do. So first, I have to tell you each dot is an election. So each dot is an election, and the distance between dots suggests how far they are from each other. However, we're embedding a hugely dimensional space into 2 dimensions. Obviously, this picture contains errors. So one has to actually look at actual data to get some conclusions. In particular, you may want to wonder, I'm somehow not getting the right thing, but, you may wonder how come this area is empty. It actually, normally it wouldn't be. I just erased with a graphics program what was there originally. I'll show you that to you later. However, there are some important conclusions that you already can draw just by looking at this data. So first of all, impartial culture is a really small island, and it's actually not such a varied set of elections. I mean, if you think about it, it's kind of obvious, but I mean, we can see it now plainly. On the other hand, the urn elections are actually covering quite a large area. And that's, I somehow, before doing this work, I didn't think very highly of urn elections, and yet they actually are more diverse than I thought. But the most interesting thing is that if you look at, if you look at Mallows elections with small values of phi, they actually form this really tiny islands, and this whole area of Mallows land is kind of winding strangely in separated islands. These islands actually don't seem so small, but this is the artifact of the program. So we are getting, the islands are much smaller. Okay, if we only generated urn model, we would get something like this. So it looks nice. If we only generated Mallows models, then if we chose the phi value uniformly at random, we would get the picture on the left. And the problem is that we get very few elections near impartial culture and lots of elections which are nearly identical to each other. If we choose this exponentially, the value of phi, we get a better result. Okay, we want more. Since I have only 5 minutes left, I'll assume that we probably more or less, I think Ulle is showing that actually not 5, I should just stop now. We will go very quickly through a set of single peaked elections. So what's important is that we use a Euclidean model. So in the Euclidean model, each candidate, each voter is a point, and the distances are essentially generating the preference order. We're also looking at single peaked elections, and I presume that probably everyone knows them. Except we use 2 models of generating single peaked election. One is the Konitzer model, where we choose the top and then we somehow extend, like here, extend at it. We use Walsh model when we draw these elections uniformly at random, or preference orders single peaked uniformly at random. And I have to mention Single Peaked on Circle by Dominic and Martin because they're here. I mean, because it's important. Okay, and we generate elections using that. We get the map, the kind of distances in the matrix. And this is technical things that you have to see to trust that we're not liars, but what you really care about is the map. And now this is the full picture. There are some really interesting things here. So of course, whatever I showed you before still holds. The few things to look at that are somehow unintuitive is that the area of single peaked Konitzer elections, so the kind of probably the most typical way of generating single peaked elections, is completely intertwined with one-dimensional elections generated uniformly at random, whereas the Walsh model is actually right here, very close, really very close to the Mallows model. It's possible to actually explain this theoretically, why this happens. The less obvious thing is that somehow, if we look at Euclidean elections, and instead of seeing, sorry, I'm somehow not. Okay. Instead of so if we look at two-dimensional Euclidean elections, they are around here. Then 10, 20, 5 dimensions are getting kind of, they're clearly separated from one-dimensional ones. But the thing that's actually really amazing is that Spock election, single peaked on circle, is actually completely around impartial culture. This seems like an artifact of the model. In fact, it's kind of, it is. It can be explained, but it actually has meaning. And this meaning comes when we ask, what is this map good for? Well, we can, for example, what we did is we run Harmonic Border on these elections. So Harmonic Border is essentially a computationally difficult multi-winner voting rule. We run ILP solver, and the darker a point is, the more seconds it took to compute on a given election. And as we can see, if we are around the impartial culture, it takes a lot of time. And as we move away, it takes nearly no time. It's kind of amazing that this is captured by this metric. On this plot, you see, again, distance from impartial culture and logarithm of time of computing. And you can see that it nicely decreases with distance. And there's not a single case of a faraway election that takes a lot of time. So we actually, somehow by accident, we got a predictor of the running time of ILP solvers on elections that can be computed quickly. Okay, we also run these elections for some two approximation algorithms. So essentially what you see here is that red dots are where one of these were better, blue dots are where the other one was better. I still have 2 seconds left. I guess Ulle, would you allow me to bite into questions a little bit? I actually
Another 2 seconds, yeah.
Okay, so essentially what you see on this picture is that it's not always as beautiful as before, which means that here, for example, we don't see a structure, but it's still extremely useful because we see that one of the algorithms is actually doing very well on 1D elections, and the other is doing much better on multidimensional elections. You would have never thought of that without actually trying. And here you can see it immediately. That's why this set of elections is useful. Now there's also plenty of other slides, which I will show you in a kind of fast forward way, just so that you can ask questions. Can you please show that to us more? So how robust is the map? Well, this was the metric we used. If you use a different, much simpler metric, we got a very similar map with some interesting features. The Mallows models actually now are circles rather than islands. But at least there's some hope this is robust. If we try other election sizes with 20 candidates, we're still getting a nice map. With 10, it's getting a bit less pretty. With 5, there's something, maybe not the best thing ever. Conclusions. This map is a useful tool. It gives you insight into statistical cultures, and it gives you some idea of how to plan your experiments or even how to present experiments. So while we would be really happy if someone used the map in their papers, at least they should maybe run their tests on elections from the map so that they would tell them what to focus on in the actual paper. Big open question is, what the hell do we do with approval elections? This becomes a generalization of isomorphism problem, and it's computationally tough. I think many people have somehow done it in other communities, but not with this purpose. So there is hope, but we don't yet have a good answer. Our software is available on Git. Not full version there yet, not without typos yet, but it's there. And thank you very much.
Thank you very much. If you liked it as well, you can unmute yourself and clap into the microphone.
Thank you. So these maps are obtained by projecting n-dimensional space to 2 dimensions and large using some algorithm. What if you project to 3 dimensions instead? Then you get something that really looks like a brain, but maybe more informative. Okay, so we did try some mappings into 3D. The problem is that actually the only way to get any idea of what this 3D does is if you're able to hold it with your mouse and move around. Then you start seeing the 3 dimensions, and we haven't done too much of that. It seems that, I mean, it indicates places where really we can't feel 2 dimensions are really not enough. So for example, for mallows, it's clear that they kind of take a different path. So we tried this a little bit, not very much. And more importantly, you have to keep in mind that the map is a toy. This is a visualization that allows us to kind of get better idea of what the matrix of distances shows. But this toy can actually be misleading. So for every single conclusion we gave you, we actually verified this with the metric. And that's how you have to do it, because there always will be some problems. Okay, I'm looking at the next question.
Yes, please do.
Excuse me? Ulle?
Please do. Please just pick a question, yes.
Okay. Question, in the slide comparing the metrics, there is a bulge on top of the linear part. What does it mean? I'm afraid the short answer is, I don't know. We essentially, I mean, we more or less took a subset of the elections that we used for the whole map. Of course, we generated much smaller ones. We measured Pearson correlation coefficient. So more or less, we got the point of, let's see, of believing, so the Pearson correlation coefficient was, I think, above 0.9 here. So this is probably, I mean, maybe we should have, but we have not looked what this bulge is. So I'm sorry, I just can't answer any better than that. It's worth looking there, so thanks.
Is it not an artifact of the size of the elections you have
I think there is
experimented
actually a
on?
strong effect of size. With larger elections, I think we would see a more linear picture. But so we tried I think 8 candidates and maybe 100 voters. And then, for example, it was nearly linear. So the size actually matters. We stayed with 8 by 8 because somehow 8 by 8 looks like 100 by 100 in proportion at least. Okay, the questions are flowing, so let me try to...
Just pick any you like.
Who drew the monsters? I did. Monsters are Piotr. Oh, yes. Thanks for the apostrophe and not just monsters are Piotr. Okay, Bill Zwicker. Swap distance is... Or maybe I'm just looking at the wrong place. I was kind of looking maybe...
But these are very good questions. You just pick any of those.
Okay, sorry, I thought I was looking into area that was throughout the talk. So swap distance is squared Euclidean distance on the hypercube. Border distance is squared Euclidean on the permutahedron. Have you tried this distance? No, we only, at least I think not, unless one of these happens to be the second distance we described. So not yet, no. I mean, so far we have only found 2 distances that were feasible computationally for this size. So I guess I'll get back to Bill asking for the more or less for some details, and if we manage, we'll compute it. Reshef, suppose I run simulations in some empirical paper. Do you think a good use of your map would be to cover much of it, instead, for example, trying many different cultures with many different parameters? So the way we envision using the map is, of course, you could just run on the map. And when you run on the map, this gives you some kind of hints of what you actually need to be looking at. Because, for example, if we were doing a paper on speeding up solvers for harmonic border, then after showing the map, we would say, okay, this is obviously the slowest case is impartial culture. And after that, we never look at other models again. We just do impartial culture. So I could imagine that you might not even show the map in your own paper. You simply say, we looked at this map, we did this experiment. This is why we're looking at mallows with this parameter and that parameter that pointed out there. Of course, if you do use the map, it can maybe help readers. But the price is, of course, that you have to explain a bit more about the map. But at least you can draw it for your own experiment with our software. Question from Ilan. Do you have a characterization of big holes or properties of big holes? So again, this is, keep in mind, the picture is just a visualization, a toy. If there's a hole, it's probably there is something missing there, but certainly we don't have a characterization. And we can essentially, if we look at the map, let's go to the map, not this one. For every place on this map, for example, if I want something here, I can take this election, and I can mix them half-half, and I will get a point around here. So I can always fill in places in this map by simply mixing several models, which is also why we did not mix mallows models. This always works. This simply, I mean, more or less this is how metrics work, and the fact that our metric is not very complicated.
I suggest you take one more question, and you can also later respond to a few more on the chat, of course, offline.
Sure. So the question from Yair, if I saw correctly, how robust is the map to different embeddings? Well, if we run our own algorithm a few times, I mean this Fruchterman-Reingold, it gives pretty much the same pictures or very, very similar, sometimes rotated. Obviously, these things can rotate. If we use other algorithms, things can be very different. And the Fruchterman-Reingold algorithm is somehow achieving a compromise between mapping the distances properly and drawing a nice picture. So that points don't overlap too much. And so we thought this was a good compromise. If we use an algorithm completely focused on maintaining as good distances as possible, we will probably see something somewhat different. That's why, as we said, the map is a way to look at the results. It's not telling the full truth. The full truth is in the matrix of distances, and as truth happens to be, it's ugly. I mean, it's impossible to kind of get easy conclusions from it. So we get conclusions from the map, we verify them on this. So thank you, Ulle.
Thank you very much, Piotr. Let's take the speaker one more time. Okay, so now we're going to try a novelty. We're going to try to simulate the coffee break feeling for you. As you know, in any good conference, the highlight are the coffee breaks. This is not going to be any different here. If you're talking to yourself, please mute yourself first. That would be easier. So what we're going to do is we're going to create these breakout rooms, and we're going to put around 10 of you in each room. Now you can choose yourself. Do you want to have a real break and you go away for 10 minutes and check on the kids, go to the bathroom, whatever you have to do? Or you click, yes, I want to enter this breakout room. Then the screen will go white or black for a second. Don't worry about it. Then you enter this room. You can talk to the people there. If you don't know what to say, maybe just say who you are, what you're working on. If all of you do that, the break will already be over. If you feel like it and you have some ideas to exchange with people about the format of the seminar, and this happens to be discussion about that, please send me an email afterwards about your findings. So we're going to pause the recording in the main room now, and Dominic will now send you to the breakout rooms, and I'll see you in 10 minutes time. Is it working? You're off. You're muted. Yeah. Okay. Yes. Yes, I see your screen. We're still going to wait a few seconds before I introduce you.
Okay. We can see the screen, but it's not in presentation mode. I think it's fine, but if you have very
yes, but I think it should stay, it will remain like this because it's easier for me. You know, I'm technologically not that advanced as the Polish people here, so sorry for that.
Oh, this looks good.
Yeah, so if it's good for you, I'll keep it like that, yeah?
Yes, I think it's good. Okay, I think everybody is probably back. So then I'm going to introduce our second speaker for the day, which is Clemens Puppe. Very glad to have you here. Clemens is based at the Karlsruhe Institute for Technology. Many of you will know him for his work on all sorts of axiomatics regarding strategy improvements in voting, judgment aggregation, diversity. Maybe you have read about that as well. Besides that, maybe less well known in this part of the community is his work on his experimental work, so behavioral economics type of studies, also very interesting. Also some of it related to topics in social choice and fair division, these kind of things. He's one of the editors-in-chief of Social Choice and Welfare, the journal. So that's, of course, also something that's relevant for many of you. And today he's going to tell us about the median voter theorem and what happens to it when it suddenly may cost you a bit of money to vote. So Clemens, please go ahead.
Yes, so thanks very much. Please note anytime that you cannot see slides or do not hear me or something like that. Well, let me thank the organizers so much for this. I think this is a wonderful idea to have this kind of seminar, and I'm very glad to be part of it. So thanks very much. This is joint work with my PhD student, Michael Müller, who is also present and who will try to answer questions in the chat window in case you have questions, and he will perhaps interrupt me if something is not clear. So let me go to the matter. So it's about strategy, proofness, and participation, and here is our motivation. Now we have this wonderful property of strategy proofness. Why is it wonderful property? Well, because when we take a collective decision, we want to judge, we want to assess the outcome, but of course, relative to the true preferences of the people. So strategy proofness guarantees that you know the preferences of the people who voted, because usually we assume that preferences are private information. So if you want to judge the outcome of an election, you better know the preferences of the people. That's the rationale why you want to have strategy proofness. But of course, and then we have these wonderful results, and one of this wonderful result, I will present you Moulin's characterization of all strategy proof social choice functions when you have single peak preferences. But these results usually assume that all people participate. But that is by no means guaranteed. And actually, I know of many cases where people rather do not participate in collective choice processes. For instance, if they have high costs to do so. So the second property that you would like to require from an election is that people really have an incentive to participate. Now, our motivation was the feeling that perhaps there is a tension between these two incentive properties of elections. Because very intuitively, you would think, well, all these strategy proofness results rely on the voting mechanism to limit the power to influence the result for a voter. I mean, at least in some sense, right? I mean, there is this property of uncompromisingness, perhaps that you have heard, which simply states that, for instance, in the median voter rule, you cannot pull the outcome closer to your own peak, right? By exaggerating your peak to the side where your peak is anyway from the outcome. So strategy proofness relies on limiting your influence on the outcome. But of course, participation relies on the fact that you do have an influence. If you don't can influence the result of an outcome, why take part in the election? So there was this intuition that there maybe is a tension between these two properties. And the answer is yes, there is. And here is the main result that I want to present to you. I have only one result, this one. Suppose that all agents have single peak preferences over the level of a one-dimensional variable. So this is a special case in which we know that there are strategy-proof social choice functions. Also assume that no two agents have the same peak. This will be the generic case. I mean, if you have a continuous line, the generic case will be with a finite set of voters that no two agents have the same peak. We can discuss what happens if, okay, you have to, I mean, it's an assumption here. Let's take it like this. Now, what we assume that is voting is costly, but according to a mechanism that is strategy-proof, anonymous, and responsive. Responsiveness is a very simple condition. I will explain it in more detail in a minute. It simply means that if all voters shift their most preferred or shift their vote in one direction, then the outcome should react to this. It should not stay the same. Okay, so this is a very weak responsiveness condition. If you have these three conditions, then we show that there is a unique equilibrium, at least a unique equilibrium in which every voter plays a weakly dominant strategy. And in this equilibrium, at most one agent actually casts a vote. Okay, this is the result that I will present to you. And then I want to discuss it with you. What is the implication of this result? Now, just for comparison, suppose that you have a cardinal scale on this one-dimensional variable, so you can add numbers. Then you could think of other rules that are not strategy proof. For instance, the average rule, right? So every voter casts a vote for the level of the one-dimensional variable. We take the average. But surely this is an anonymous way to determine the result, and it's responsive. If all voters increase their vote, the average will increase, but it's not strategy proof. But for sufficiently small cost, full participation is generically actually the unique equilibrium under the average rule. Of course, it's not strategy proof. People will not vote sincerely, but they will exaggerate their votes, but at least they will participate. Okay, so I look if I see some questions for clarification. Let me just look at this. Yes, it is complete information. I will come to that. Yeah, it's a complete information setting. Yes. All right. So what we do here is we bring together two strands of literature, and I don't have the time to go over the literature in 20 minutes. Let me just tell you that this will be the paper that we will rely on, Moulin's characterization of strategy-proof social choice functions on the line under single peak preferences. The second strand of literature is the pivotal voter model, right? Which has, of course, examined how people's participation decision look like. But the pivotal voter model mostly takes two alternatives and assumes majority voting, either under complete or incomplete information. There are very few exceptions from these two alternative setting. And the one that is most close to our work is the paper by Osborne and others in the American Economic Review of 2000, where they also look at voting with single peak preferences. If you're interested, I will explain to you what is the difference between our work and theirs. Mainly, they assume that people vote truthfully, even if that's not an optimal strategy, right? So they don't have a micro foundation of the assumption of truthful voting, whereas we do, right? Because we only consider strategy-proof rules. I can come back to this point, perhaps. Vince asked about neutrality. No, we don't need neutrality. You will see exactly what's going on in a second. Anonymity is just enough here. Okay, so let me go to the model and then derive the theorem and even say a little bit about the proof. So we have a one-dimensional space, let's call it X of alternatives. Agents have single peak preferences. Pi is the most preferred alternative or peak. And here is what we assume about voting costs. We really have a minimal set of assumptions that really says there is some cost. It could be small, but there is some cost in voting as follows. For every fixed alternatives, all X, right? For every fixed level of the alternative X, all agents prefer the outcome without participation to the same outcome when they have to participate, okay? But that's more or less it. More we don't need to assume. There is one thing we assume in addition, not to make the result trivial, namely, we assume that each agent prefers to get her peak with own participation to the outcome when nobody participates, right? I mean, we need to assume something about the nobody participates at all, and we assume that this is a bad outcome. Okay, so here is the example that we want you to think of: a faculty meeting on a Friday afternoon. The level of the variable to be determined is the budget share for the academic guest program. Well, we have Friday afternoon, and of course a COMSOC video seminar is not a good example because it's so much fun to participate. But this is a faculty meeting. That's a different kind of thing. Okay, so that's perhaps the example you want to think of. The model, it's a complete information, as I said, complete information setting. Okay, trimmed mean, I will come back to that. I have 10 minutes to explain the result. I think it will work in 10 minutes. There are two different ways to model this. I mean, you have to somehow model the timing of the process. The simplest model works as follows. You simultaneously decide whether you want to go to the meeting on Friday afternoon. And if you decide to go, right, you meet the people there, you see who is there, and then you vote again in a complete information environment. You know your colleagues and you know their preferences. Notice that under strategy proofness, it's a weakly dominant strategy to give your true preference anyway. So this is not so much of an assumption, the complete information here. I should also say you can also model all things simultaneously to have simultaneously the decision to vote, to participate and to vote. It doesn't really matter, again, because of this weakly dominant strategy. This is explained in the paper. But to keep things simple, think of the model as you decide first, do I want to go to the meeting? Everybody does that simultaneously. Then people show up at the meeting, they see each other, and then they vote optimally according to the voting mechanism. All right, a voting mechanism here must specify what will be the outcome for any possible set of participants, okay? So by N, this N is the set of potential vote participants, then the set K shows up, and the social choice function Fk must tell you what is the outcome when the set K of participants is there. We will require this function Fk for each set, non-empty set K, to be strategy proof, anonymous, and responsive. Okay, strategy proofness is clear. I will not explain it. Anonymity is interesting here because it also implies something not only for the mechanism given the number of participants or the set of participants, but it also implies that the mechanism should only depend on the number of participants and not their identity. So in other words, if K and K prime have the same number of elements, I require the mechanism, the social choice function for these K, for this set K to be the same as for the set K prime when they have the same number of elements. That is a restriction, and it does work here. I should note this. Finally, the responsiveness condition is if all participants increase their vote, the outcome must increase as well. Okay, now, which kind of mechanisms satisfy these three conditions? Well, Moulin tells us how do the mechanisms look like that are strategy proof. It's the generalized median voter theorems. You take the true votes of the K participants, V1 to VK, you add K plus 1 phantom voters, yeah, and you take the median of this 2K plus 1 numbers. Now, the responsiveness does the following here. Namely, such a generalized median voting scheme is responsive only if all the phantom voters are at the extremes, right? For simplicity, let us consider the compact interval 0, 1 as the outcome space. Then the responsiveness condition, that the outcome always reacts to a unanimous shift in all votes, that means that you must not place a phantom voter somewhere in the middle of the line. This must not happen, because then you could construct situations in which all voters increase their vote, but the outcome is the peak of a phantom voter, right? And that's why you cannot place any phantom voter here in the middle, right? In the interior of the interval. They must all be at 0 or 1. But you cannot place all of them at 0 and not all of them at 1, because then again, the outcome would be non-responsive. So at least one phantom voter must be at 0, at least one at 1, and the rest must be distributed in the extremes somehow. That means that you have just one choice here, namely the order statistics. Okay, so the order statistics are the only strategy-proof social choice functions that are responsive, and that gives you more or less the result. So you can either choose the lowest peak, the second lowest, and so on and so on. Now, again, the theorem, I've shown you this theorem already, but now I think it's clear, or it becomes plausible why it could be true. Just a second, there are some, okay, 5 minutes left. Okay, so I should be quick. All right, so I repeat the theorem here. There is a unique equilibrium if each voter is really playing a weakly dominant strategy, which is truth-telling here, of course. And in this equilibrium, exactly one agent casts a vote. And now there is one additional information here, namely, it is either the voter with the lowest or with the highest peak, okay? Which is bad news, because if you want, for instance, to implement the median, right, you could be very far away from the median voter here. And notice the only assumption is that we have small epsilon costs. Here is the proof, very quickly, 10 seconds. The point is, in the case of two participants, you must decide if you want to choose the lower or the higher peak. And you have to do it for all two participants in the same way because of the anonymity assumption, okay? So with two participants, no matter who the two are, you either must decide to choose the lower peak, right, or lower vote, or the higher vote. If you decide to choose the lower vote, then of course only the voter with the lowest peak has an incentive to participate in the election, because every other voter who will jump into an election where only the lowest peak guy is in will not change the result, so he will stay at home by assumption, right? The interesting part of the theorem is that there are no other equilibria. Right? I mean, that there is this one equilibrium is somehow not so surprising. What is a bit more surprising is that there are no other equilibria here. All right. Now, to end, you could then say, well, wait a minute. This is simply because of tie breaking, right? This is an artifact because with two people, you have somehow decided how to break ties, go for the lower or for the higher peak. Now, a probabilistic mechanism could solve the problem, right? By saying that, okay, if you have two people, then you just determine whose peak will be chosen by a fair coin. That works. The question is, can you mimic somehow this in the deterministic setting, for instance, by using the symmetric median rule? So consider the symmetric median, that is the standard median if the number of voters is odd, and the average of the two middle votes if the number of voters is even. Now, of course, this is anonymous and responsive, but it's not strategy proof, right? Because in the case of an even number, you take the average, and when you take averages, you create an incentive for the people to exaggerate when they believe that they are above the average in one direction, or in the other direction if they believe that they are below the average. Nevertheless, you can say something about the equilibria under the symmetric median rule. And here is this proposition, which, however, also tells you that the result is somehow not very attractive. If you use the symmetric median rule and you now have to assume something about the equilibria, namely assume, let's say, subgame perfection and some coalition proofness properties, let's say strong Nash equilibrium in the voting game, then you get that either the game has one single participant as before, or you have an even number of participants and a fixed outcome, namely 1/2. Okay, this is, I think this is more surprising, this result, than the main result. But the main result, and I'm done. This is my last slide, and I see Ulle smiling. Okay, of course, what we assume is deterministic voting here. And we show that there is no mechanism that can reconcile strategy proofness and participation. The responsiveness condition is not really the guilty part. It makes the result very clean and crisp. But even without the responsiveness condition, you can always find profiles where only one individual will participate. As I said, probabilistic voting rules can reconcile participation and strategy proofness. And that's it. Thanks. Right.
Thank you very much. Very good. So we have our 10 minutes for questions. There are several interesting things in the chat. I wasn't always able to follow, but Clemens, if you want to pick a couple of things there and just see if you can answer, and otherwise people can also raise their hand. And if we have nothing to say, I will pick on you and ask you to ask your question.
Okay, let me see, where can I start? Yes, onto is fine as long as one phantom is at 0 and 1. Yes, the responsiveness condition, I should say that, guarantees efficiency. Okay, so that's one thing. Mixed also, yes. There's a unique equilibrium, right? There are no other mixed equilibria. If only the votes above. Okay, this already Michael has answered. To handle ties, what happens if we have an additional phantom with a top in that case who steps in? Well, yes, but the question is again, where does the additional phantom step in? He must step in at 0 or at 1. There is no other way. So this does not really help. Just a second, I lost now the chat. How do I get back to the chat window? Here.
Click on chat at the bottom.
Yeah.
Click on chat.
Marcus, the result is driven by the fact that an abstention is treated as abstention. But what if instead any voter who abstains is assigned a predetermined default vote? I don't know. I don't know. I have to think about that.
They abstain, effectively they're voting, they're misrepresenting preferences, and they can't do that in a strategy-proof voting rule, right?
Yes. Yes.
So you force them not to abstain.
Yes, that's right. That's right. Okay, then there is okay. You think about incomplete information. All right. Now, incomplete information, yes, there is one thing to worry about. If you are, so the incomplete information does play a role in the participation decision, right? But it does not play a role in when you have met the people then, right? And you see who is there, you know that a strategy proof rule will be used. So you tell the truth. I mean, that's independent of the information you have about the others. But of course, in your participation decision, you make you have to somehow form a belief who will take place in the voting. Yes. So incomplete information is interesting. We haven't solved that so far, but this is something to think about. Equilibria and mixed strategies, again, as I say, in the main result, it does not play a role. Okay, here is a good question, and I would like to talk a little bit about unique peaks. Well, yes, the entire literature on the pivotal voter model lives from the fact that when you have, let's say, two alternatives and you do majority voting and you have many voters, then of course you do have mixed equilibria, because now it's really a coordination problem, right? You have many people preferring one candidate, many people preferring another candidate. Now is the coordination problem, who goes voting in order to, right, equilibrate the opinions. And this is a very interesting literature. It lives from the fact that many people have the same peak. So by contrast, what we are doing is we are assuming that there are much more alternatives than voters. So the generic case will be that two voters have different peaks, right? So there the artifact would be that two people have exactly the same value of the level of the variable, and they know that they have the preference for exactly the same value. So this is really not telling something about this pivotal voter setting where you have many people who vote for candidate A, many people vote other people, but also many vote for B. So these are really two separate problems.
So Neil, I think maybe this was your question, or do you still have something else? Then you can unmute yourself and ask the question.
No. Yeah, it's just this. I wanted to know the setting for which this would be more useful.
Yes. No, this is really a setting where you have many more alternatives than voters, right? This is this is only for that setting. This is useful what we are doing.
Okay. If somebody wants to raise their hand, I will call on them. Don't know if there's still stuff in the chat that Clemens hasn't reacted to yet.
Okay, I'm looking for things that yeah, I mean the last points in the chat I think I addressed. Is there a difference if X is the whole real line versus positive half line? No, there's no difference. I mean, it doesn't really matter whether you have an unbounded or a bounded line. That's not an issue here. Vince has the following. Okay, let's take positive and negative values. If all votes have a positive peak, take the min. If all are negative, take the max, otherwise take 0. Yes, that violates the responsiveness condition, right? Because you take the 0, right, in one case, no matter if someone has voted for 0, right? And this then creates a possible for non-responsiveness. So that's ruled out actually.
That's right. And I think Mike already responded to that.
Oh, I'm sorry.
But then I was wondering, so is the responsiveness condition maybe a little bit stronger than it appears, right? Because if you limit it to say that it only applies when voters move, but they're already close to each other.
Yeah.
Right? So it's like almost like a unanimity thing. Then you can get around this.
Yeah. No, I would not say. I mean, the responsiveness condition simply means that for all profiles, right? No, for all profiles of preferences, you get the result. If you don't have the responsiveness condition and you place, let's say, a phantom voter at 0, then you still can find profiles where you have to place the true voters so that all the phantoms are outside the true profile, right? And then you get the result back, right? So as soon as you have a profile such that all true peaks are between all the phantoms, right? In an interval of phantom voters, then you get the result back. So what the responsiveness condition does is it gives you the result for all profiles instead of for a subset of profiles, okay? But without the responsiveness condition, you still have subsets of profiles where you have single participation.
That makes sense.
All right. Okay, let's thank Clemens again.
Yeah. Thank you.
So that was great. That brings us to the end of the seminar. I still want to make a couple of announcements. So somebody just in the chat asked me or mentioned maybe it would be good to make the log of the video chat available. We do that. So if you go to the recording of last week's talk, you will see the chat next to it. And we're going to do the same thing this week as well. It may take a couple of days until it's online, but it will be online. I now see people answering how many people accepted the invitation to go to the breakout room. So it seems around half of the people. And also, yeah, so roughly half of the people were left behind. Yeah, so maybe this was reasonable. With 5 people, you can have a conversation. So maybe we'll continue doing it like that. If you have other ideas, please feel always welcome to send us an email about it. Couple more things. If you haven't noticed yet, on the website of the seminar, there is now a mailing list that you can subscribe to that we will use only to send reminders for the seminar. So 1 or 2 days before each seminar, we send one email. Please don't miss this edition. So you can sign up to that. You can also find on the website some fancy stuff that integrates the seminar into your own Google Calendar or similar things. Also on the website, there's a little poll that you can indicate whether you think the duration for the standard seminar as we have it now with 2 talks of 20 minutes plus 10 minutes question, whether you think this is right or whether it should be longer or whether it should be shorter. So it's very useful if you can click on one of those. I think that brings me to the end. So I'll remind you that next week, same time, we have 2 speakers, Agi Che and Remzi Sanver. The abstracts are on the website, so you can have a look. Looking very much forward to seeing you all there. We again are going to keep the session open for a few more minutes. If people still want to type something into the chat, say something, you can do that. And then I see you all next week. So thank you very much. Bye.
Thank you. Bye-bye.
Good to see everyone.
Bye all.
Bye all.
Bye.
Bye-bye. Piotr, I really like your talk. Is there some place to see it in like a very long version? Like I could listen to it for 90 minutes easily.
There is no long version of the talk, but
Okay.
it's actually, I mean, so I guess right now it's technically not possible to read the paper, but I can send you one. I mean, there's
That's
only
good.
one, but
Yeah.
so I guess it will become available soon at AMAS. So Staszek will actually be giving the AMAS talk. So.
Oh, nice. There'll be an alternative interpretation of the paper.
And most of the slides here is different. So,
good,
I mean,
good.
the data doesn't change. The picture stays the same, but the comment is different.
I guess the map could be rotated just for some novelty.
That's true. That's true. Especially that it's in New Zealand, technically. But
And I guess it would be good if you like invested in like Oculus VR glasses, so you could look at the 3D model at some point and see whether it's
right. Yeah, we played a bit with 3D. It's actually less appealing in my taste.
right. Yeah, can imagine.
Yeah.
Okay, Ulle is bored with our conversation. All right. Bye bye.
Yep. Thank you. Thanks a lot.
Thank you.